¿Qué tal? Buenos días a todos de nuevo, tras la fantástica ponencia.
Good morning, everyone. We've all thoroughly enjoyed Javier's workshop. We had a little bit of a technical hiccup, which was fortunately solved quickly. And then, just before lunch, we will be stopping later, logically. But before we do so, we have another fantastic presentation delivered by Laura García Leiva and Pablo Liébana. They will be telling us about defense and security and high availability for the new firewall generation in Linux. Can I ask you, how many of you are familiar with iptable? How many of you are familiar with Netfilter? How many know about nftables? Less people in that case. So, during our presentation, we will be talking about why we need an evolution of iptables like it happened in Linux. And then we know that nftables has to do with users, performance. We'll be covering all of that with all details about those different areas. My name is Pablo Neira. I'm working for Netfilter. I've been with them for some 7 years, and my role is checking everybody else's work. I check the patches on the email list integrated within Linux core for IP filters. And then we also have user areas. You probably know about that better, iptable tools that will be coming up during our presentation. I work as a lecturer at the University of Seville, and I'm also part of a spin-off where we're developing all these ideas, software implementations for systems that can be deployed on the internet. My name is Laura García, and we're here on behalf of CBNet. Zevenet is a product, is free software, and mostly it works with load balancing to avoid servers being stressed out, and they might crash in that case. Also, we want to have a high availability and load balancing, and we know that Netfilter has different tools available, and then those that were missing, we have been adding thanks to the Linux core and Netfilter. This is the table of contents for our presentation. We'll be explaining first what Netfilter is, its infrastructure, including kernel space and user space. We'll be explaining all those components, how it works, the data pathway, since you get your card. Then the difference also between iptables and nftables. That is quite a broad area. If we have time, we will have different demos for firewalls and load balancing and the load compatibility. You will see later how you can then migrate to nftables. So let's start with infrastructure of Netfilter. Let's start with a little bit of background. I also want to tell you a little bit about another piece of software at the beginning of Linux. At that time, we would just copy what Unix had. Before that, there was a different software, but the first one that was really popular was IP chains, with a short life because tables was launched almost straight away. So IP chains, that option was pretty quick to come up, and we kept on the Linux tree the compatibility layer like we have now between iptables and NF, which is a basic layer for migration. Anyway, there was a compatibility layer that continued for quite some time, and then iptables was launched in 1998 just to give support to IP4. New requirements came up quickly, and then it was important to filter IP6 at a time when Linux implementation was very rudimentary. And then it was just a copy-paste solution to give support to the filtering of IP4. So that was a bad start for the design pattern. iptables then, iptables, sorry, rptables, ebtables, and IP6 tables. So what's been happening in the coming years? Well, trying to unify from the development point of view, because where there was a problem on iptables, they had to be corrected. And IPset came later with ippool. The idea was that there was a new number of sets, and at that time the system was not so small anymore. There was more and more confidence and trust, similar to the situation now. But that was a very initial period where the idea was that we could group different IP addresses using trees, for instance, for range implementation, or spread. Because finding and matching the scalability is much better than checking a list of 1,000 different rules, where you had to check one at a time, one after the next, and that obviously takes a long time for package processing, and that's different for the filtering performance. So that was the extension of IPset, the new one, and after that new tools with a system which is not very well known, but it's quite popular. iptables users call it match state. So we have the connection tracking, an engine that checks the flows, and I say flows when I mean transit connections. So that implementation had to be improved with well-defined API tools for synchronizing status and synchronicity. All of that work was done at a later date, and it took a little while to be introduced properly. And then there was a big leap to 2013, when nftables has been included in the 3.13 kernel. So during our presentation, we will tell you about what iptables does with all that expressiveness and power for that new tool. If you have any questions, just let us know anytime. That's true, because we don't want to be talking for 2 hours non-stop. We want your feedback as well. So, different components of Netfilter. I don't know if you can see the text from the back of the room. You have the other screens closer to you, that might help. We have the darker lines to separate the kernel space from the user space. For nptables, users are in orange with different possibilities. iptables, rptables, IP6 tables for, and also IPset. All of these tools, or most of them, send a very long message with all the information for the rule that you want to have at the kernel level. There's a long message sending to the kernel space to different modules. And you can see different boxes there for IPT not, IPT mark for flows or packages, IP set for the setting part, IPT cluster IP for cluster generation or virtual IPs, then IP with limit for connection limit, IPT contract for matching that, the multi-port here for matching different ports, the proxy area so that packages can be dealt with at user spaces. Anyway, here we have a list of just a few examples, because iptables, in fact, has over 100 available modules for matching and manage different packages. Apart from that, at the bottom here, we have other modules of the kernel in blue, and those modules share all the Netfilter infrastructure, both for iptables and for the green area that we will see now. So where both infrastructures are used, where is that? Well, in the connection counter, in the NUT infrastructure, the logging system, that's common as well, SIM proxy, NFQ, different examples then. And I just want you to understand that within the kernel we have modules that are specific for nftables, for also for with part of the infrastructure that's shared. Then in the user space here at the top, here we have the area for nftables, and for the user space you can see there how components are fewer. nftables with user commands, nft symtec for rule replication, or lib nftables, that's a library where user spaces can connect to that to launch NFT commands. What's the main difference here? That communication between user spaces and nftables is done through nflink. And what's the difference between using blogs or netlink or nftable tools? You will see that later, the reason for that, but I just want you to bear it in mind. Well, let me just add a few details. Laura said that nftables rewrites the framework, and that means we can classify the traffic. We're not using anything else here. It's not like we've scrapped everything to write everything else. It's just the package classification framework that we've worked on to solve problems, so that for the next 10, 20, 25 years we can continue to work with firewalls. iptables is fairly simple compared to nftables. nftables is like a compiler, and we will see how it allows for scripting, still very basic, but more functionalities will be added little by little. And then the scripting and compiling functionalities works with a rule-based language, which is familiar for administrators. And that language then generates a bytecode, which is expressed in the virtual machine in a format called netlink, very common in the core, in the kernel, to work with Linux. The system is based on messages. We start with a message, we say what order we're giving, and then different attributes are added with information expressed by the rule. I say, I want to add this rule, and I want it to work with this, that, and the other. These are the options that's sent to the kernel, and then it creates a native element and adds it to the corresponding list where the different objects are kept. So, as opposed to the interface we had earlier, because in the past we used to have a binary system, a binary format sent to the kernel where all the rules are expressed. For instance, when we want to change one single rule, we need to get from the kernel all the rules, and then the kernel replaces the old rules by the new rules. In nftables, we just send a message with a new rule we want to add, and then the kernel can reconstruct internally. So we'll be talking about that on the next screen slide. It gives us a lot of new possibilities. In the user space, we also have contract D. That's an element so that the user can communicate with the contract. That's important for both infrastructure. And then block D, an area for the user where from the kernel we get all the blocks that we need when rules are matched. Can I just say that iptables compared to NFT, the base code for NFT is much smaller. The area in the kernel is much smaller on nptables. We have 101 different extensions, all of them matched with a file on C, whether it is match or target, where we can fit information that can be generated during execution. On NFT, because it's a virtual machine, we have a set of instructions, round about 30, 40 instructions that can be combined so we can express and tell it what to do with the rules. It's much more expressive. So the 100 IP code modules might end up as, what, 20? Yeah, a much smaller number of instructions. So what is the data pathway on Netfilter? On the user space, we do control play to communicate with the kernel. On iptables, on nftables, we're explaining internally the data flow within the kernel when a package goes through it. Well, the letter size here is far too small for you to see. We'll try to explain what this says. For instance, in blue here, we describe the different steps on the link layer. Here we have the network layer, that's IPSs. In yellow, we have the protocol. We know about the ports there. And in pink there, we can see the application layer. So that would go directly to the user space. So on the left, we can see the access through the card of our package, any old package, which gets to the Ingress area. That's the first step. Then that's where the package accesses our system, our device, and that's where we can filter. That's right. And this is something new that nftables has. We didn't have this on iptables. Early on iptables, what we had there was bridge checking and then filtering. But with nftables, we can start filtering much earlier, at an earlier stage, which means that filtering is much faster. You will see later that the performance during this stage is quite amazing, and the properties are pretty impressive at this very early stage, so we can match many options there. Once the bridge is checked, the package continues all the way to the Egress stage with the card output, or here with the raw table without contract. And then we would say port guarding, that would go to the user space if we have a web server, and so on. Finally, when the package is ready to come out, we have the output tables here and post routing. That would process the packages so that data we need would be ready with the origin IP and so on. Let's look at some examples next. We would have two different types here. The data path at the server with a firewall, for instance, or with a web server. In this case, we would have, for instance, a web server with a firewall. In this case, it would go through all the layers, getting to the application layer, finally. And then it would go to the web server. That's right, Ingress, where traffic is filtered, then going to the pre-routing chains before the routing decision. And once the routing decision is made, because the environment has the firewall at the back end, at the web server, that means the traffic is going to a process that's working on the process. The routing would say, hey, this is my process, so it would be routed upwards. It would go to the input table, to that input chain, and then there would be the firewall rules that we want for the local system, and if that goes through okay with a policy, we would look out for the socket associated to that package. That is, if there is a process at the user end waiting for packages to be processed. Then if that goes through, the process would do the processing. It would say receive, and that's where reception of the package would take place. So there are a number of steps before the package gets to the user space. And I've often seen on the internet situations where somebody recommends that input filtering should be done for a web server. Well, in fact, filtering can be done much earlier. Instead of doing it at input time, it's much more efficient doing it earlier at pre-routing. So the earlier you filter your package, the better your performance will be. And why do we care about performance? For instance, if I have a DOS attack, then you would need more resources. At the end of the day, legitimate users would not get the service. So the earlier we do the filtering, the less resources we'll be wasting, and attackers know about that. So all these chains can be filtered at different stages, depending on the path that the package follows on the Linux stack. So the more instructions are working, that will have a negative impact on latency, on our band, which is what matters for package filtering. Here we have another example, a perimeter firewall, not offering a web service. We don't need it to go to the input area. It goes through forward, it stays at the lower levels. Processing of filtering would happen there, going through forward to output, so that connection could be redirected to the web servers or whatever other service the data flow, in this case, doesn't go upwards to the higher layers. That's right. We would just stay at level 2 or 3 for forwarding. So it would go forwarding, pre-routing, forward, output, out. Out it goes. Sorry, routing before pre-routing. So Ingress has to do with OTC. I don't know, TC, sorry. I don't know if you've ever worked with TC. It's not great fun, to be honest. People go to internet scripts, they install it, and developers know TC is not easy. But anyway, it's an alternative to TC Ingress. And I would also like to change your mind a little bit talking about Ingress, because filtering traffic at pre-routing stage, sometimes people go to Ingress and they make a mistake because you have access to all packages, they think. RP, IPv4, IPv6, everything that's on the Ingress pathway. And a typical mistake is not allowing for RP traffic, and then sometimes people report, hey, Ingress is working. That's not true. It's just that the Ingress policy was too restrictive. So you should change a little bit the way you do that. Is a new way of linking that's interesting, which is why more and more people are using this idea. The earlier the filtering, the less instructions need to be read, and the system will work better. So let's see now the difference between IP tables and NF tables. If you have used IP tables in the past, you probably know how it has quite a lot of limitations, mostly in the most complex environments. Let's have a look at the most obvious one. NF tables is just one single component for user space that replaces IP tables, IP6 tables, RP tables, EB tables, and IP set. For instance, if we want to drop with all of them, we would need to execute a command, make a command work at all those levels. Whereas with NF tables, we just have one single command, and configuring the family that we want to do the dropping with, that's enough. So that really simplifies the number of rules that you need to use and have on your firewall. That's right. Tools, we used to have 4 tools, now we have one single one. Although there are slight differences from one tool to the next. NP tables, for instance, the syntax is different. On NFT, we have homogeneous. It's more homogeneous. Now, rules are more unified, and we now have INET with one single rule. In that case, we can filter traffic coming from either of those 2 families. For those of you who work on maintenance on IP tables and so on Debian, on Ubuntu, on Fedora, well, that makes their life so much more simple. In the past, we had to have different people doing the maintenance of these tools, whereas now just one single person, one can do the maintenance. Another important difference between them, and mostly for those of you who want to migrate IPv4 to IPv6 or having both stacks and infrastructures working together, well, NFT tables is definitely the best tool for that type of maintenance. Why? Because in the past we needed 2 different commands, different stacks, different rules, And if we wanted to use the same rules, we had to duplicate them, whereas now NFT includes the init family that can see things from both stacks. So if you're going to have on your service both IPv4 and IPv6, you just need one table, an inet table. You will be able to see all the traffic and manage the rules all at the same time. Another important area of complexity that systems administrators often complain about is that they had to duplicate their filtering policies if they worked with NP tables for filtering for IPv4, IPv6. At that time of transition, where you continue to work with those two families at one single time, that was an additional burden. With front-end tools like Thumb, I don't know if you're familiar with it. The idea is that one single configuration would then generate rules for IP tables and IPv6 tables. But from the point of view of unification, it was just for the front end, not for the kernel, which has its limitations. The inet families then allows for traffic, for instance, for port 60 with just one single rule, saying, hey, I accept traffic for the HTTP port that's not encrypted, and one single rule can just give you your firewall policy. Another important difference is that IP tables, by default, generates the usual tables. For instance, we can see the pre-routing, input, output, and post-routing tables, how they're generated by default. So when that happens, packages access those hooks even if we have no rules. And that would slow down the data pathway, even if we're not using the hook. On nftables, the difference is that we can self-configure all the chains we want for packages to see. For instance, I can generate a chain on the routing hook for a TO, for instance, with this rule here. So all packages that get to pre-routing, I will see them and they will try and be matched to that rule. Look at this other chain here that I've generated. Well, that's not linked to a particular hook. There will be no traffic there on that chain. So other chains like output or routing that are there by default, well, in that case, it won't make me lose performance. That's right, IP tables are used to detect chains by default, even if they were not needed. And a lot of users complained about poor performance. Whereas now, only the chains that are required are considered. It's much more simple as well for people to understand how it works. Also, on IP tables, there was a list of tables. When you wanted to eliminate those, you had to execute delete or flush before you could eliminate it. And that's for all the tables that are generated for AP tables, NAT, Mango, ROAR, filter, all of those. That was in the past, whereas for NFT, you just need to run flush rule set, and all the rules, all the tables we want to get rid of, just go. then NFT table net, anything like that. All of those managing those rules is much more simple. Now, about the design for NFT tables, that's definitely. It's also improved the interface for us to talk to the kernel and communicate incremental changes. And now, where firewalls have to be dynamically updated for the maintenance, for instance, of blacklists and whitelists, well, changes have to be done on the router all the time. In the past, IP tables had like 600 different ones. In the past, you just had to load the firewall once and that was it. You could forget about it. Well, not anymore. And about the concurrence, the improvements, back in the 1980s or in the 1990s, users used to work with IP tables, whereas now we have third parties that have to invoke NP tables from the commands. Well, that used to happen in the past, not anymore. And the interface for blogs is very limited. So if there are different applications and processes in competition, one particular process might lose out. The blog needs to be downloaded again, recreated, and introduce that in the kernel. So if there are different processes competing to add rules, if one of them gets the block and adds it to the kernel again, well, if another process has been faster, that first process has to again download the block, send it again, and then the updating of rules time-wise is not deterministic, and you can't calculate how long that will take. Well, not on NF tables anymore. Another problem we used to have is the loss of internal status. Thanks to counters, NP tables has solved that. The problem is that I get the block from the kernel through the firewall policy to add a new rule. As long as I'm at the user space, packages continue to move and circulate and updating internal data on the firewall policy. And then when there's a new firewall policy, some of them were restored, but a lot of them were lost. And typically, we know now about the Quota extension, which allows to fit packages up to a certain level or quota. On IP tables, when firewall policies had to be updated regularly, users used to complain that quota was lost or wasted. Getting the block, reconstructing, and adding that to the kernel again. Well, that's improved with NF tables. So let's not forget that attackers might know about all these weaknesses and make the most of that to attack your system. For instance, the Docker infrastructure that uses IP tables internally for networking, for routing and filtering. QNT, for instance, uses different processes to update rule sets that only have to do with one container. But at the end of the day, that might hurt the whole node. Those are limitations that have to be solved on NF tables. In the practice, not many users have reported these problems because use has to be pretty intensive with many processes updating very frequently. So sometimes people have solved the extension rudimentary so that all of that was not lost. But NF tables, with its new interface, solves those problems natively. We also know another difference is that now we have a more natural, more expressive language, so that the number of rules can be lower, because more rules means lower output or performance. So with a more expressive language and by using rule specifications properly, we can end up with far fewer rules on nftables. Sorry, the sound is not working. Oh, now it is. That's right. Both actions can be combined. We can see this example, all of that combined on one single rule. We have the log option for log messages, and then the action.
If you use the log as you see on that rule, all the packages will be matched before checking whether they are on status. If we add the log after the set state established, once we know that that's a match, there is the log, and so the action order matters because it reads from left to right, and everything having to do with actions will follow that order. Semantically speaking, it's just the same as with iptables. And on nftables, we don't have targets or match. We only have extensions, generic extensions. There's no difference there. And it's just another thing for development. On the framework, there's just extensions. Extensions. Sound is off. We're sorry about that. So back again. Back on again. I forgot what I was saying. Okay, targets and matches. Yes, that's right. From the point of view of development, frameworks unified it because we would see the extension separation compared to what actions we have, because there are some extensions where we need to match and perform an action. So that's been taken out. That artificial separation has been removed. New structures, map, sets, and native decision maps structures. We will move out of sounds off again. So step by step we will closer to more advanced structures. This is still a very simple example, but here you see a set declaration, what we call anonymous or nameless. And the idea would be to first decide the selector and then on the other side also the values we want to fit. So instead of 3 rules that we can have, there's just one rule to pull together all those values that we want for that given field. Here you have an example of sets, but actually for the maps we can type key value, and so we can have a destination IP depending on the source IP of a different element. Even through the data path we can dynamically add to a list, whether a black or a white list, but again dynamically we can set all the source IPs that we are interested in that match a given pattern. So it makes it possible to have a static set match against that set, but also from the data pathway as well we feed back into these structures. Ingress, yes, this is some information on the new Ingress hook. This was a tiny benchmark of ours that is pre-written traffic filtering. And then from Ingress, same rules on nftables, twice as much performance. And then Ingress with a set and a list of ports. And there you see that the set performance is very similar as if it had just one value. Again, another reason for filtering from Ingress, another reason that is. Well, difference is twice as fast for filtering raw pre-written. So what if we had a DOS attack, you can have your machine go surfaceless if you filter way after Ingress. So we use half as much resources to cover a similar amount of packages. FastPath. It has NFT, and well, it has several fast paths or fast track routes to expedite packages. What we are saying here, that is 2.75 times faster than before. And this is for a fast drop-in of all connections coming on the other side. Usually this is costly for the system, and with Ingress we will move all that information, those are packages or flows that we want to drop, and we will move them up to an earlier state. That way we expedite the message drop-in or package drop-in that come to forward. Simple idea. If the package follows all these paths here, the whole path, all of it, that would be lots of code to run. That would be the classical forwarding Linux path. So it's very intuitive. So the shorter the code for a package to be on a port, on an output interface, so the shorter the time for the decision, the greater the performance. So instead of following the classical path that it's Ingress, pre-written, forward, post-written, and package out, and the package going through the whole stack and all the validations on Linux, all the software processes in the processor, instead of that, just a small number of packages will follow the slow classical path for every validation, and so it goes through Ingress, pre-written, forward, and output. As soon as with our policy we say this flow has been validated, so it's a set of packages, let's say the first two packages in both directions, or once we have the TCP enlargement, or once we have the application data on TCP and we've realized they do make sense. Once we've done that, we can set the flow onto a table, flow table that is, and on that flow table, that's Ingress, and it will annotate what's the port and the destination NIC, the interface. The following packages will not follow the classical pre-written, forward, post-written way. This is also a search in the table. You need the pre-connection tracking and every rule and all the code. So we get a package, we see whether it is a flow. We are saving ourselves time and expediting the forwarding path using software. This is a feature that can be combined with hardware. NICs and switches follow tables, infrastructures, and hardware which are programmable from the point of view of the driver. And so instead of adding just entries into the float table in our piece of software, we can place them on the NIC. So without the processor, without the OS, it is on the destination port. Of course, there is some security implications here. But from a number of packages that would be decided by the admin, so it can be set up as part of the firewall policy. From that point, we lose control of the flow because it goes onto hardware. So there are some security implications. On the other hand, it's all expedited. Here we see a good degree of Installation options. If it is too costly, we can use the classical Linux way. If we want to expedite it and keep control on software, then flow table on software, which is Ingress, and that way we know what to do with it and where to place it. If we want to expedite it with hardware features to remove load off the processor, then on hardware, because we can trust that flow. It's been secured. We have 3 degrees, and that's the idea. Fastpath. Fastpath is not an idea of ours. It's been discussed for long now, and it's been used elsewhere. So what we've done is we've developed, try and see how we could integrate this into a Linux ecosystem as a good match to what we had. It had to make sense. This is part of the kernel now. It was added a year ago. And this is one of the features on nftables, and you have the documents on how to set it up. It has all been done. The software support, also the offload support as well. And this is under development, and some manufacturers are trying to add compatibility here. Some extra data on performance. Here we have some figures on IP tables. We can move around. With an Intel 5 machine, we can use 1 per core. So with an X number of cores, we would multiply by that number of cores up to 256,000 HTTP requests per second. If you've ever used any firewall for user space, they'll never go as high with performance. So web servers, for example, for filtering at that level, we can go up to a few thousands per records per second that can be filtered. So if we use the kernel and we do it at an earlier stage, we manage to move around several 100,000 packages per second. Full flows of HTTP flows. With IP tables, we got twice as much. Whether we're using destination NAT or source NAT, we can really change this all. But basically, that would be about doubling or tripling the performance that we were getting with IP tables. Actually, for user space, we could not go as high as that. Ingress, then, why so interesting, and why is it so good on IFT? Because we can move around 7 million flows of HTTP flows per second, which that's per core, by the way. So if we have a 4-core machine, these would be multiplied by 4. So those are levels, or well, this is a performance that is way higher than if we were to filter on pre-routing or on raw or other subsequent layers. We should not forget that there's a before and an after when we talk about CPU vulnerabilities with meltdown and Spectre. And Linux community has paid attention to that. It has an impact on processors and systems inside the kernel. So finding a solution to those vulnerabilities is actually a high penalty for Linux kernels and operating systems. Red polling has been a high penalty for operating systems. Can go as high as 20% penalty. So red polling, if you see how on other tables we can move from a penalty with the same benchmarks without the patch and with the patch to solve this. So from 40% of penalty to 17% penalty with NFT. So thanks to a careful implementation with these vulnerabilities, we are reducing penalties for this action. This is development level avoiding indirect calls. Here you have an example on how to set up the fast path, as we've said before. We would need a flow table on Ingress book. We choose the devices or the network, the boards on which the Ingress hook wants to read the incoming packages, and then for the string we set up on forward hook, we choose a rule stating that everything that follows this pattern, which is protocol TCP protocol, will be taken to the Ingress port. Well, yeah, the idea would be to define the flow table. You register it, and once registered, you see what interfaces are part of the flow table, and then with the policy that we choose, we decide when we will be adding the flows to the table. This is quite simple for any TCP traffic. So the first two packages here, one in each direction. From the second onwards, this is added to the flow table chart, and all subsequent packages after that will follow the fast track. Scripting, as discussed by Pablo with iptables, well, there was no other way around it. You needed to have iptables save, where you would have a file with all the rules that you could reload for the booting time, or else use a bash script with every rule that are sequentially run. With this new scripting system for NFT, we actually have a language of its own, user-friendly for the admin, and so they can have their own rule set. Here we would use as an interpreter NFT. We can include other NFT routes. We can define variables that we will then use for our rules. As we said when we started, NFC is supposedly to have more scripting language rules. It is always rule-based. That's the basis here. And why is that? Because, well, probably you might say, I used to do this, where I can do it using bash or SQL script and play around with it. But that splits the atomicity of the rules. So if you add a bash script on iptables, you have invocations to independent rules. So with every new rule, they are all run one by one. So the blob is updated, then the next one, then the next one. So it's not that all the rules are added at once. So if you have packages moving around, there is a firewall policy that is not coherent, is not consistent. That's why we've always encouraged not to use iptables as part of it. Because everything done here is uploaded atomically. If a rule fails, none will be run. Yeah, that's it. Everything inside the file is logged into, and all the messages sent to the core are built and sent at once. And we also implement 3 options. So after all these messages, there is a commit message That's the semantics for that. So everything you do, you implement it now. And we also have the dry run method, which is the firewall policy, but do not implement. I just want to know whether it would run. And with our new API, semantically, it's been defined. This is a whitelist example. Yeah. This is a whitelist example. Here you have a simple use example so that you see the difference. Up there you see a set where we've integrated port definitions that I want to allow. A second one, we called it whitelist, and it's a rule set that has been created, and this is the FUD table. Because we are very clear about FOO table, sorry, because we see that these are not preset. I want to register whatever I want, the strings, the tables, and I name it whatever I want. That whitelist will save IPv4 addresses. And as for the rule, for every rule that match this here, no condition, by the way. So if they lead to a given IP destination on the set, on the whitelist set, we will count them, the packages, and add them. So I can create an empty set first, that where I define the rules for that set. So every match, every hit will be based on that, or will be assessed based on that, and then dynamically we can add and delete IP addresses. Next one is a typical example. There are well-known scenarios where system administrators want to map different network segments or some masquerading on a public IP. On IP tables, you need to define one rule per segment. If you only have a few that will go through several NATs, only a few rules are needed. But if you have thousands and thousands of rules where you need to have intensive mapping with different private segments and public segments, these would be lots and lots of rules to look into with the sets. The set infrastructure allows for maps and dictionaries. I'll explain that. And with this map, we are building. What we do is we define a map where the left side is what will be matching, and what we are matching is the source IP. This is a source NAT, which is a conditional one based on the source IP, and this is explained here. So this is the syntaxes, which says I need a SOS NAT, sorry, post NAT, and you will do that based on the source IP, which is a given segment. And with that, I use the IP for the updating of the source IP. Yes, dynamic whitelist, quite similar. We define a set once again. Here we use a timer, so after an hour, the elements inside the set expired and are deleted automatically. And we can add some starting elements. Here we add a standard or a rule, which refers to that set. You see, update says update the set. So this is an update on the path. Whenever there is one package getting there, it will remain the whatever we want. So from this package that we want to update, I will do so by extracting the source IP. So we are populating a pool based on the source IP, and we populate this whitelist. Here we also have a preset timeout, but we could have a specific timeout for some rules. So we have a global one, but we can fine-tune it, and for some segments that we don't trust, we can narrow it down. And well, this is the white list, so less aggressive. But if it were a white list, black list, it would be shorter and more aggressive. So we have this degree of customization that we can change based on the packages on the net, on the internet, using any kind of matching criterion to add elements. With dictionaries, we can solve some bypassing. So we can define what was known as user strings. On NFT, this goes away because they are all user chains. The user defines all the rules themselves. So these are base and non-base chains. The basic chains are the ones on a hook, and there's traffic going through the data path. And the non-basic or non-base chains has a rule that states there is some bypassing, and the package starts by looking into those. Here we have a simple sample. What we'll do is, based on the IP protocol field on this package, we will dump, and we will have the firewall that we can use for TCP traffic. We can have one for VP or UC or UDP, and so on IP tables we would need three rules for the dump. If it's not UDP, ICMP, and if it can take any other protocol, I would specify it. So these are 3 rules. Here, just one, and on the dictionary we find where the dump is. This kind of an example we will use for load balancing, because we will match services and jump to backends or balance standards that will refer to backends. We'll see how it is very useful for setting up load balancers.
Another novelty has to do with concatenations that can be done on any meta information that's generated. So we can configure and set the selectors for chaining. You can see there with the ports. The idea is that for chaining, we would match the pair made up by 2 different components, and if there is a good match, we would go to the white chain list. And then, depending on the situation, we would go to any other chain where the flow could be processed differently, looking more in-depth, maybe by suricata for intruder detection. And although for data processing that's a little bit too much, well, all of those ideas could then be combined with what we mentioned earlier. You can combine, chop and change, and you have like a framework as if you are playing with Lego blocks to then define our data plane. Here we have some examples. For instance, we can do chaining with address, for instance. That's right, MAC is used to then populate a set. In this case, we called it bar, and that's where elements are added. As we said at the beginning of the presentation, comments are important on IP tables. When you have firewall rules, with tens of thousands of rules, sometimes it's good to remember why a rule is there, and it's much better if it can be done natively on the firewall policy. So comments can be added both to rules and to sets. Here in this example, we can see this rule saying that any traffic going to quadruple 8, a Google server, will be accepted. That's a way of accepting DNS requests on Google. You can also use it to build a blacklist. For instance, traffic will be accepted for these IP addresses. For instance, IV4 for addresses there. So comments can and should be added. A user case that users also often request is modeling the sets after the DNS names. That's the typical way of referring to firewall policy. On IP tables, behavior was not quite good for users, because filtering is not by name, but rather IPv4, IPv6, level 3 at the level of the internet, and that was pretty confusing on IP tables. Working with NF, we say that users should define sets, giving it a name that has a connection with a service provided, for instance, www.whateverwebsite.com. And those servers would have a set of IPs. So on the user space, there would be something to populate the sets and fill it with the IPs that correspond to that name. And then the set would be used. Do you follow what I'm saying? That's a way to ease maintenance of the firewall policy. That's our recommendation, at least. And now meters and quotas with a name. Sorry, counters and quotas with a name. We can name counters. Here we see the table filter. It could be bar or anything really. Here the counter is called HTTP traffic. That's a counter that can be referenced on our firewall policy. This rule says that for output, any traffic going to HTTPS, we should have the counter name as HTTP traffic. So there's an extension called NFACC for accounting, and yet you need to add a rule for every object to be counted. NFT has a huge advantage because that can be combined with maps and sets. And let me just remind you that the firewall policies, NFT administrators should update it and reevaluate to see if they can make the most of their sets, so that you can condensate and simplify any rules that are duplicated unnecessarily. Here we can see an example map where the name of the counter will be updated and obtained depending on the IP destination port. So I would use the object HTTP traffic to count the traffic. So we would be updating, for instance, HTTPS traffic with 443 or HTTP traffic with 80. Why? Because they support the atomic fetch and reset. That means that we can bring the name of the counter and reset it. It's like going with your wheelbarrow, then empty the counter, then going to the user space, generate statistics, whatever you need to do with that, and then setting the counter to 0. So it's a functionality that's very common for accounting for traffic, and that can be combined with the ideas of chaining and monitoring. That's right, it's a statistical function for monitoring. So now maps with counters and names. Right, let's keep going. This is getting a bit harder. It's the same thing as we saw earlier, but now dynamically. We generate a map where on the left we have IPv4. And we need to say that for this IP address, we're going to be using this object to update the counter. We have generated two counters, computer 1 and computer 2. So computer 1 is updated when traffic comes from 192.168.23 from that system, and for the same thing for the other counter. So the map can then be updated and refer to all those situations. Another important difference comparing IP tables and nftables is that with IP tables we used to, if we wanted to integrate the application with rule running or execution, we had to call system from Python, from some other program, from Perl. And nftables has a native library that allows for an includer to be done. This is an example here on C, and nftb, which is the balancer for nftables, uses this particular infrastructure. The idea is that your program should include the library. You then generate a context object, CTX. We then set that in a string buffer, or the commands, well, it could be commands or it could be a chain of commands that need to be run. For instance, here, nft flush rule set, and then semicolon saying that we want to chain it with another rule. In this case, nft add rule, filter, input, whatever. So this is a static string, but it could be done dynamically by using other functionalities depending on the program. Then once the buffer has loaded the whole string that with all the commands, all the rules separated by semicolons, we then launch it to the context variable. We send the buffer, in this case for CMD. We specify the size of the buffer. And then here, this would be run or executed going through all the NFTL libraries, then kernel security, and we would then get the command. We would then release the context, and our program would then connect with NFT to apply rules from the program. That's right, because we shouldn't forget that we have an extension on Python that is integrated with a JSON representation, where you can include your firewall policy, and then you can call for rule updates. That's how those solutions might work. Even we've used the lower level library in this example, but there's also support for Python that can work with JSON, and all you need is an API network to be able to work remotely. The idea is that you would need to add the code on Python for implementation to be possible. So the starting initial infrastructure allows for third-party integration at a lower level on C, or more modernly so with Python. Do you use, it's just to tell you not to use certain user commands. We're going to leave the demos for last if we have time for them. This is the idea for the demo that we have prepared, but if you have a particular user case that you would like us to check, we could use that for the demo. If anybody wants to ask questions or doubts before we start with the demo as well, now would be the right time. Sorry, unfortunately there's no microphone. The sound is not reaching the booth.
Claro, la heurística la tienes que definir ya tú. O sea, aquí la infraestructura.
Well, you would need to define that. The infrastructure allows for metering, and then if you have a software to monitor the higher number of packages, because administrators play with that a little bit. They know how many packages tend to go through every hour. They know the profile, normal profile. So if they see something that's out of the ordinary, the tools to be able to detect that would be included here. This is the generic infrastructure for package integration. So we can use it with third parties that use heuristics. And that can be used to get the value of the counter. And there's a request that we got, which is having a threshold over and above which notifications and alerts should be sent. And there are extensions that are allowed for that. But we could also have a threshold above which user space intelligence would then decide that firewall policy should be adapted. The firewall allows for that.
Uso que queráis comentar o sí. Si quiere un micrófono.
We need a roving mic, please, for questions.
¿Veis por qué el performance es muy importante?
We can see why performance is pretty basic in what we do.
Bueno, el performance es importante, pero nosotros también
Performance is important too, but in our project we really care about usability, which is why your feedback, your reporting on anything that you feel that makes the tool harder is really welcome, because we're talking about a command tool. It's very, very important for us to learn more from you about usability. On error reporting, for instance, the tool should have more and more the possibility to send alerts, which is a little bit what's been missing from prompts in the past. For instance, the system telling the user, hey, what about using this? Making suggestions and prompts so that the infrastructure allows for it. We just need your feedback for us to know what. We've seen the difference between nftables and nftables, but we now have a more dynamic development. That's the main difference. Do you think that nftables could be used as an IPS or an IDS? I can't see why not. The framework would allow for extensions to be added, so we could download IDS work within that framework. Modern IDSs can do all sorts of things. For instance, the typical benchmark is Suricata for open source free software. We can have more and more options for pre-classification at a very, very early stage. And pre-classifying then can really increase scalability of what we do. But I can't see any reason why this framework will not become more expressive for intruder detection. We talk to the Suricata team, and that's something we've been debating, and I'm sure that's an avenue that will be explored in the near future. Any more questions or comments, or a particular user case that you would like us to explore with our demo? Well, if that's not the case, we will now talk about the compatibility layer. Because right now you have your firewall all set on IP tables and you're working well with that. But how can migration can be done at a productive environment to nftables? The main distributions like Ubuntu, Fedora, and so on include that compatibility layer, although users often don't realize it's there. Look at this. We have two basic types that you can use, and they have good usability, in fact. You see, you could have the iptables translate command. Use that. If you have a script that runs on iptables, then you would replace the binary iptables by iptables translate. And also, if you have commands with IPC tables, in that case, you would replace it by IPC6 tables translate. So the rule would then automatically be translated, and on your script, you would just do that replacement, and in rebooting, if nftables is installed, the rules will be working. But iptables and nftables are incompatible, as in you can't use them at the same time. So if your system is working with iptables, you should first install the compatibility layer so that those rules would be working. But on a computer where only nftables was installed, you would then have to replace, as we said earlier, and then as if by magic, your script would be working on the other one. On iptables, this is very simple. The syntax would change and be translated for nftables for IPv4 and IPv6. That's right. The typical two commands to save the firewall policy would be iptables save and iptables restore, and those two generate a file that we can then transfer to iptables translate, and I think it's -f that gives you the translation for all the extensions on iptables. And for those of you who use iptables, all of that happens at the user space. The translation operation doesn't modify the firewall policy. It doesn't touch anything that you might have deployed. It just translates the file for that file that works on iptables 6. And if all those rules can be translated natively, then the system will suggest which rules are suggested. If anything doesn't work properly with the translation, please let us know. And there are very, very few extensions that we don't give support to yet, but it will tell you, look, this extension I can't translate, so that you know what percentage of your firewall is not supported natively. We are currently giving support for some 90% of the functionalities. We have very few still to complete, and the least common ones, in fact. The translation. I just wanted to explain that it's one-to-one mapping. That's one rule is translated as one rule. There's no grouping of rules as yet. That's something that we want to do in the future. So the admin would need to do that, see what rules could be grouped together as a set. But the translation is one by one. So if you have 1,000 rules on IP, then on NF, you would have still 1,000 rules, because it's much more expressive. That doesn't make any sense. So that's why they should be grouped together where possible. Instead of iptables translate, you could also use the compatibility layer, and that would require, well, we had this graph with all the different components on Netfilter, and then using all the tools there on the user space, on iptables, the kernel time would be captured and they would be sent to NFT compact, that compatibility module, using nftables internally. Many of the most important distributions are already using this compatibility layer, so you're probably using it as it is, even though you don't realize that the NFT infrastructure can work with those commands. That's right. You can even check if you're using the legacy infrastructure or not. The user would be using iptables rules, but as far as the core is concerned, it would not be. They would be nftable rules. The idea is that there will be just one single implementation at the core level, so that if there are no incentives for users to migrate from iptables to nftables, well, they're not going to do it. So we want to make it easier and more interesting for users and for us as well, because we don't need to continue to have two base codes, maintenance. We want to in the future just focus on NFT, and then for libraries and everything that has to do with the user, well, as far as users are concerned, is iptable syntax, but not for us, is NFT. Here we can see an example. I don't know if you can see this from the back of the room. Here we have the iptables minus a forward, well, the syntax on iptables, which then generates with iptables save this file here. When we run the file with nft pull reset, we would then see the rules and the chains, the strings that have been generated with iptables. In fact, internally are seen on NFT. That means that at the kernel level we're using NFT, but the syntax is using iptables. This is what is happening at the moment, so that users who have not adapted yet to NFT syntax can still make the most of the new infrastructure at the kernel level. That's right, continuing with compatibility, and iptable syntax expressiveness is rather limited. You can do what you can do, and you will see as soon as you start using NFT what I mean. For instance, as Laura said, a rule on IPT, quite simply, what happens is that the user thinks and feels that they're still working with IPT, but they're not. Running behind it or in front of it is working on NFT. For instance, NFT rule set. If you type that, well, you will see they're there. Why? Because there is a certain level of interaction between those two systems and the same infrastructure at the kernel level. Once again, we just want to make it easier for users to migrate to the other system. Does that mean that both modules are compatible? No, it does not. For instance, if we load iptables and nftables, well, you're doing something wrong, and you will see how rules don't behave properly. That's right. If policies are not compatible, logically, if you're using iptables at your legacy and then you want to use NFT, you won't see the data pathways correctly. You won't understand what comes first or last, so that's not recommended. But the system still warns you. It tells you, hey, you're mixing NFT here with IP table legacy. Just for you to realize that you should do the classic IP table save for you to see the firewall rules, just making it more simple for users to dare migrate. Now, so any further questions or comments? Do you have a particular user case or do you want to know how to do the migration from IP tables to NFT? Where's the roving mic, sorry, for questions? Gracias.
Vamos a hacer más rápido.
Mi pregunta era...
Well, I have a question because I don't know if NFT has been tested for mitigation tools, for instance, DD2, which I think that works with IP tables fine. Has that been checked with nftables, or would we do it with the translate tool? Now, filter 1, I think, has support for NFT, as far as I know, and it could also be used natively, as long as the compatibility layer is there. That's right. The implementation of NFT can group, for instance, for blank list maintenance, and I have seen cases. I can tell you, this morning I got up very early, so I feel a little bit confused. I think I've seen there's support. That's right, it has been done.
Bueno, vamos a hablar ahora del balanceador de carga.
Let's talk about the load balancer here. This is a user case, so that we can use the nftables, the infrastructure, to generate a load balancer. Have you ever used a load balancer, whether it's with IP tables, whether it's LVS, or maybe at the user space level with some kind of software? Well, we can generate a very efficient load balancer thanks to all the tools and new properties included within nftables. We have managed to make it so that it can help not just for firewall, but also for load balancing. At the kernel space level, there are different ways to work with load balancing. One of them would be working with LVS, this virtual server that has been native since the 1990s, I think. LVS is an implementation within the Netfilter system, although there is a different group of developers in charge of maintenance. It really uses infrastructures that have been generated on Netfilter, and then there's a different type of infrastructure they set up for duplication, for more specific load balancing, so that you don't need to use the more generic things that have to do with firewalling. LVS also has a structural design that is a little bit peculiar. It does basic checking at the kernel level. That means the kernel space, sorry, there's a mistake up on the screen. It says user space. It should be kernel space. What it does is launching packages to know if the backend is fine. If you want more advanced checking, then you would need to work at the user space level. Is this a reasonable design? No, it's not. Checking should be done not at the kernel space, but at the user space, so that it's efficient. Another problem is that it's not capable of doing the more complex task. It really depends on Netfilter. For instance, a transparent proxy, or it doesn't work well with multi-ports. You need to first label the packages so they can then be processed properly. It has limitations with multiple protocols and so on. iptables can also work with load balancing, and at CBNet we've been using it up until now, although not very efficiently. Why? Because you need so many different rules for every backend server. We need to include, there was at least duplication. So if we have 100 backends, we would need to at least have 200 rules. And those are rules that are computed sequentially. So you can imagine performance is lower and lower as you get more and more backends. Other problems are blocks, and, well, a number of them. So what we proposed back in the day was having an nftable design that was better, so that at the user space level there would be the control play so that packages could be processed, and the data path of the packages is done at the kernel level, and then NFT, which is like the devil, defines the rules required for load balancing. Then the health checks can be done at the user space level, talking to the devil and saying, hey, activate or deactivate this backend so that you can change parameters for the different servers. So at the kernel level, what happens? Well, just load balancing. What we managed was modeling and designing with NFT and providing support to most of the topologies that can be used at the production level. We haven't been told about a particular topology that we don't maintain. SNAT, DNAT, DSR. And let me just stop here. Is that DSR is a return that's used for balancing on Google, where Magler balancing is used. And what it does is using DSR structures to simplify the traffic that goes from the backend to the customer without going through the balancer. So huge infrastructure, for instance, for Google or Facebook, they use this system because performance is far greater, and it's one step shorter because the response from the backend to the customer doesn't go through the balancer. On NFT, we can work on Ingress, so that's super fast. Managing multi-ports and multi-protocols happens natively. Here, support for IPv4 and 6, or virtual services are indexed with VMAPs. Once again, that adds speed. We don't need to sequentially process the rules. We just have a rule with different parameters on the map so that we can balance a number of virtual services at the same time. There are different types of programmers here, depending on the weight, or sequentially, also hash or symmetric hash for IPS. And thinking about the control plane, what do we have? Well, a daemon at the user space area communicating with the kernel through nftables through that infrastructure.
So this daemon opens a socket, an HTTP socket on JSON, and you can set all the features for the virtual servers and the backends. And now we are integrating at the hackathon everything having to do with security into the daemon. You can also have server losses set up. The pJSON is there and you can automate it and send hot commands. But do not forget that when you send a hot command, you need to make sure that it doesn't shut down your connections. That will be persistent between client and server, but it needs to update the parameters without having an impact on service whatsoever. And also a security key so that not anyone can send this API command. Let's move on to some examples or a demo. I think we have 20 minutes left. We can run a demo. Maybe you are interested in a specific user case for load balance, no? So let's move on to the examples right away. Oh, I don't think you will be able to see this. How do I pan it out?
No.
Vale. ¿Quieres mostrar una demo?
Would you like to show a demo? That's our GitHub. That's NFT. Well, NFT LB uses the whole infrastructure for NFT. You can see it here. Now we already have rules that we have applied for load balance. And let's remove this. Once we flash, we've removed every rule, every table, everything we've built. Obviously, we can flash it instead of using a rule set that removes it all. So we can feed it, I don't know, X or X rule and X chain, X and Y. Usually we choose the table and the chain name. Just the same here. Instead of NTF flash, it would be NTF list. Let me show you the examples here for load balance, because we do have test infrastructure, which is quite complicated. Well, you can see how complicated it is. This use case that can be a load balancer, but actually it can be used for any network device you want to set up. So if we run SO0, well, we can start it as a daemon or as a standalone format. This would be a config file, and we send this config file to the daemon. That would be a source NAT, IPv4, TCP, and wait. So we send a JSON, which is nothing but a structure where we define for every virtual service, we called it pans. Can you read that? Every one is a farm, and each has several backends. We just need to define the name of the farm. We want to specify the name of the family with IPv4 and 6, iNet to see traps on both stats, virtual address, which is the IP through which our virtual service will be sniffing. On virtual port, we specify the port we want to balance. It could be, well, here you might have one single port or a list of ports, or might be a range of ports. You can combine it all as you wish. You may say, I want to balance a range of ports and then an extra port. We could set it up here if we wish. So topology, I will not go into detail, but for balances, we have several topologies. We can have Google structure, but it's different from two web servers, or maybe it takes the original IP of the client connected to the server. So many different cases, and all those types are not useful for every service or for every infrastructure. We do specify the protocol. Here we can, well, we have a TCP, VPS, FTP. Right now we only choose one with the idea of specifying a list of protocols. So there are some apps. I do recall Zip on VoIP. We use both TCP IP, so many load balancers. They check two different virtual services, TCP and UDP. The idea is to list the protocols and be able to say whether, if it's TCP or UDP through this port, treat it as the same virtual service. We can specify scheduler, which is the decision process for one backend on the other. This one would be weight-based, preset as A, and then a series of backends. Here we would specify two objects, two backends. Well, backends would just need the IP, weight, priority, and state. Even if when we send the daemon, we have this preset setup, because of pJSON, we can set hard changes of these parameters. We can end backends or remove them. We can build new services, etc. As an example, let me start this NTF list rule set. No, first flash. That's better. All right. This is a very complicated version of almost all the features and utilities we have with NFT. We're using maps here and IP tables, chaining, IP2 port. We also use others for decisions. So if it matches a port to a client, there is a decision, that's verdict. This is what's been sniffed, 111, and then HTTP, which is the service or port we've opened. It will jump. That's a verdict. It will jump onto a table. Here it would be LV01, and as you can see, we are not inserting it into a hook, but on pre-routing, everything matched through that IP and port, destination port, will be jumping onto this chain where the intelligence happens, what backend this will be redirected to. Here you have one of the simplest examples, but we have some others that are a bit more elaborate. Here we have multi-port. How much time? All right. 5 minutes. Let me show you some examples. If there's something you'd like to ask, something specific or questions. Okay, then I go on. Here we have a case which is port range. We can open a service based on a port range, which can be useful for FTP. With FTP, we have the port 2021, and there we can open both ports with an IP using a virtual service. Here we have a source NAT to see the backend of the source IP. And this is DP protocol and same features as everywhere else. There are some other more advanced features for TCP. I don't know if you have a similar service, but it has to do with using helpers. FTP is a very complicated protocol because between the client and the server there is a handshake to agree on a port. So the intermediate device, which can be a balancer or a firewall, needs to know what's the port they've agreed on, both client and server, to open it up and allow for the traffic. Otherwise, the TCP through a protocol through a firewall would not work. It is kernel layer, and so you just need to specify for the service to use the FTP helper, and it'll do the formalities. A few more examples then. So on Ingress we specify DSR, and so it will use Ingress for this method, for which we need to have MAC address data. That's why it's here, right? This is for a test battery, so we really need to have a specific MAC address specified. If it's running on production, the system, what it does is, what the daemon does is, on netlink, it logs onto the routing table, the ARP table, to see what is a destination tag. Same as with backends. Same, but for MAC address. So let's implement this one. So we've built a service and a port, but the string, the chain we are using for the hook is Ingress. On Ingress, we will see how the flow will lead to that IP and that port, which is the virtual service, and it will jump to the LB01 chain, which will run the rule, which basically changes the destination MAC addresses, rather. That's the only thing this does. And so this is a system which was not available for IP tables because we could not have the package treatment at MAC level. With nftables and Ingress, we can do it all in a very effective way at an early stage. And basically, we've covered it all. Any questions or specific examples you're interested in? I guess we all want to have lunch. If you have questions, Pablo and myself will be here. So if you have questions, anything you want to learn from us, some examples on post knocking or anything you're interested in. So port knocking or anything, we are available. Thank you very much.